Hi everyone, and welcome to our section on induction machine starting procedures. By the end of this session, you should be able to describe the two common starting procedures used for induction machines and sketch the effect of using these starting procedures on the torque speed characteristic of the machine. So now in many cases, you don't actually need a starting procedure, a special starting procedure, because the winding resistance, the winding impedance, it limits the current that you will get. And this is more typical in smaller machines where the windings would be smaller and so they would have higher resistances. But in larger machines, when you have thicker windings because they need to carry more current, they would have much smaller resistances, and then you could get very large starting currents. So for the purpose of this analysis that we're going to look at, we're going to ignore the magnetizing current at starting, and we're just going to look at the magnitude of the rotor current. This is, well, the rotor and stator current. This is from your equivalent circuit. If we ignore the magnetizing branch, they both are the same thing. So you could look at it as the stator current. Now you'll see here that it depends R2 on S, so the current here is dependent on the slip. At starting, the slip is 1, which means the speed is 0, so we end up with this equation here. So you could see right away that by varying these parameters that we have here, we could vary what the current is. And that is exactly what we do. Our first technique we're going to look at is voltage reduction. So if we just reduce V here, we'll see that I will be reduced. And notice that the torque is also proportional to the square of the voltage, if you remember your equation for torque. So if you have, say, a 20% reduction in the voltage, then the torque will actually be reduced by 36%. That means 0.8 V squared, right? 0.8 squared will give you 0.64, which is 36% less. So if we look at the characteristic, how it would change, we'll see that if we look at Tmax, the Tmax changes according to the voltage. It changes with the square of the voltage. So if we reduce the voltage, we're going to get a reduction in Tmax. But what about the point at which this occurs? Does it change? So if we look at Smax, remember we derived these the last day. Well, hopefully you would have derived them the last day. You'll see that it does not depend on the voltage at all. So Smax is unchanged, but Tmax changes. So we have the torque reaching a maximum at the same slip, but it is now less because we reduced the voltage. And of course, we'll also have a reduction in the starting torque. All the torque right throughout the characteristic will be reduced. So the other one we typically do is the rotor resistance. So in this case, this is good for heavily loaded machines because you could actually change the slip at which maximum torque occurs. So if you look again at Tmax here, you'll see that Tmax does not depend on the rotor resistance. It depends on the voltage, but not the rotor resistance. Whereas Smax does depend on the rotor resistance. So if we increase the rotor resistance, we're going to increase Smax. And increasing Smax means it's going this way. Remember, it goes from 0 to 1. So by adding resistance, we could take the point at which the maximum torque occurs and we could shift it down to this way. So we could actually add resistance so that we get maximum torque at starting, and then we could gradually bring it out so that we maintain maximum torque at each point until we get to the operating point. Now this is only really possible if we have a wound rotor machine, because remember the The squirrel cage machine, the rotor is enclosed. We have no access to it. So only in a wound rotor machine could we use the terminals that we have that are accessible through slip rings to insert resistances into the rotor path. There is a way, however, that we could use to implement this at with squirrel cage motors, but it's a little more complicated. What you do is you use a metal for the bars in the squirrel cage that is designed to exhibit a noticeable skin effect at 60 Hertz. Now remember, when you're starting and you have zero speed, the rotor is not moving. At the beginning, the relative difference between the rotor and stator will be the stator frequency. So if you energize it with 60 Hertz, at the very beginning, the rotor is going to experience a 60 Hertz. These rotor bars here are going to experience a 60 Hertz current. And then as the rotor begins to move, what you're going to find is that becomes less and less. The frequency becomes smaller and smaller because the relative difference between the rotor speed and the stator magnetic field is reduced. So what we do is we use a metal which has a resistance which is very low at low frequencies and peaks at about 60 Hertz. So this is Z rotor. So at 60 Hertz you have a much larger resistance. Now remember, skin effect means the current flows to the outside of the conductor, which means you have a smaller effective cross-sectional area, so a larger resistance. So if you use a metal which gives you considerable skin effect at 60 Hertz, you could get a larger resistance. Let me put this as R. So it's clear that it's that we're looking at. You'll get a larger resistance at 60 Hertz, and then as the frequency is reduced, that resistance will become smaller and you will get less losses in the system, and your torque will shift, your maximum torque will shift closer to the operating point, the steady state operating point, that is. So in summary, by now you should understand the two common starting procedures used for induction machines, and you should be able to sketch the effect of these starting procedures on the torque speed characteristic of the machine. Particularly, note how the maximum torque, the starting torque, and the slip at which maximum torque occurs change for each of these two methods.